Okay, we will be making a recap on vectors in two dimensions, Newton's first law and Newton's second law, because those things we already done them during our contact sessions. So I'll be making a revision to make sense of everything. Firstly, we'll be looking at vectors. Am I writing here or what is happening? Okay, let's try to revise. We'll be looking at vectors in two dimensions. So, okay. So let's look at the main basics of this. So we'll be looking at vector. Vector, we said, is a physical quantity that has both magnitude, magnitude and direction. So basically, a magnitude, or when we're talking about a vector, we're talking about a physical quantity that has both magnitude and directions. And when we're looking at the direction, we're looking at something like left, something like right, something like upward, downward, and etc. Anything that indicated direction. But because it's a vector, and in physics we deal with calculations, we're going to replace direction with positive or negative. Meaning if the other direction, maybe upward is positive, then downward has to be negative. If right is positive, then left has to be negative. Then we'll be looking at, again, something called magnitude. Magnitude we're looking at is something like a size. It can be, for example, newtons, whatever, maybe 20 newton, can be 30 kg, and etc. Anything that represents the size and the quantity and the size and the heaviness of something, we're talking about magnitude. Then again, we'll be taking a look also on the scalar. Scalar is a physical quantity that has only what? Only a magnitude. Magnitude. So magnitude, we said what? Size. It's still the same definition. But in physics, we focus muchly on what is called a vector. Then from that instance, we'll be looking at an illustration. On our illustration, we'll be looking at an object. This object has a force acting at an angle, theta, here, has a force acting at an angle theta. Right. Then here, according to the principles of vectors, we say we resolve vectors into components. Then here we'll be having a horizontal component, which is fx, a vertical component, which is fy. Then from this instance, this can be transformed into a right-angled triangle, which is like this. Oh, I drew it very, very long. Okay, a right-angled triangle like this with a force like this can be about Fy. Here's 90 degrees. Here's Fx. Here's theta. Here's the bigger F. If you can check here, for you to find the Fy, which is your component, and Fx, which is your component, you have to use something called SOHCAHTOA. The way in which this happens is this means side. This one means opposite. This one means hypotenuse, right? Then here, this one means cos. This one means adjacent. This one means hypotenuse. Then this one means tan. This one means opposite. This one means adjacent. You see, so that is what these things means. Then from here, if you need the components can either be Fy or Fx. These ones are the ones that associate with an angle. Associated, let me just write it down. Associated with a force at an angle. So meaning the force is acting at an angle theta. This theta is with respect to the axis. So what is happening with this is that here we're gonna use sine to find an opposite. Is sine theta, which is equal to, for us to find Fy, we'll be saying opposite, which is this side, because in a right angled triangle, we all know that this is our opposite, this is our hypotenuse, this is our adjacent, this is theta. So opposite Fy over hypotenuse, which is F, then we cross multiply. We take this and multiply with that. We get Fy, which is equal to F sine theta. I advise that always when you're making use of components, start here so that it doesn't confuse you when we're talking about vectors in two dimensions. You see, so that it does not confuse you. Then again, let's wrap some things to make a space. Let me wrap these things again. Then again, if we need fx, fx is adjacent, right? We need it is a component. We're going to use cos because it's an adjacent and we have hypotenuse to be cos. Theta is equal to adjacent is fx, hypotenuse is f. We take it and multiply it there. Then fx is equal to f cos theta. Then we have this one intact. You see, this is our horizontal component. Okay, let's dive in to look in details about this. Let's look into details. Illustration. Okay. Always, if a force is a box, is acting at an angle theta, remember this force has a component. What is that component? Is Fy and Fx. The question is, we always conclude that the horizontal component is Fx is equals to F, right? More, we're going to say cos theta. And we always conclude that a vertical component is always Fy, which is equal to F sine theta, right? This F is this F, theta is this theta. And even in this side, everything corresponds according to that. But the thing is, in vertical projectile motion, this thing, it only works if they're given you a diagram like this. In vectors in two dimensions, instead of applying them like this, you need to apply them as follows. According to sine theta, which is equal to opposite over hypotenuse, and also cos theta, which is equal to adjacent over hypotenuse, and also tan theta, which is equal to opposite over adjacent. You see, according to this, you need to apply them according to this. That's why I advise that even in these situations, apply it according to this. So what's happening here is, I just want to show you something very, very nice, is that here we have a right angled triangle. Theta. Always. You know what? Here is our opposite. Here is our hypotenuse. Here is our adjacent. This is pure math. So we're going to be applying this one in vertical projectile motion. In vectors Vectors in two dimensions. Vectors in two dimensions. We'll be applying much of this principle. But if a diagram is drawn, for example, in a plane can be in a horizontal plane or in a vertical plane, this principle always applies, right? As we move on. So let's go again. So we might have an object in a horizontal plane, right? This is the object in a horizontal plane. If there is a force F acting there at an angle theta, you know that we have horizontal forces and vertical forces. According to components, we already know that Fy is equals to F sine theta, Fx is equal to F cos theta, according to components. Vertical component, horizontal component. Immediately there is a force at an angle. These components, they are always there. Then another situation, we have object in an incline. When we have an object in an incline always have gravitational force. And if there is gravity, there is always Fg perpendicular and Fg parallel. And if there is Fg perpendicular and Fg parallel, we always know that this component Fg perpendicular is equal to Fg cos theta. No, cos. Sine theta, and Fg perpendicular is equal to Fg cos theta. These things, they are always like this. They don't change. They are always like this. Immediately we have an object in an incline. Nowhere we have gravitational force that it has parallel component and perpendicular component. Immediately we have a force at an angle. You know that we have perpendicular component, vertical component and horizontal component. That is it. So if we come again and say we have an object in an incline, in a horizontal plane like this, and there is a force, always know that if the force is at an angle, we have a horizontal component and also a vertical component. Always know that. Then again, if we have a force, an object in an incline, always know that we have gravitational force Fg, which has components, which is Fg perpendicular, Fg parallel, normal force, and other forces that might be acting on an object. Then here we'll be having maybe friction and normal force and also Fg. So in this situation, remember, if they can ask you to find a normal force, always take note that Fn is equals to Fy minus Fg minus. Basically, let me write it according to the principles. Basically, we will come and look at whatever I was trying to explain here. We need to explain something first before we come there. So if we draw a free body diagram, remember, in drawing a free body diagram, the max determines how much force, how many forces you have to indicate. For this one, we're going to have an object there. Then we're going to have a normal force, which is this force. We're going to also have gravitational force, which is that force. Then we're going to have also this force, F, and frictional force. meaning this one has to be 4 marks. 1, 2, 3, 4. Because this force is at an angle, or the other free body diagram is, you choose whether you want to write a force exactly the way it is, or at an angle. If it is at an angle, we're going to have Fy going hand to hand with Fn, which is the normal force, Fg, and Fx, and again, F gravity. These ones, they take 1 mark, then 1, 2, 3, then is 1, 2, 3, 4, then is 4 marks again. You see, 4 marks again. You see, so basically you choose whether you want to write the free body diagram in terms of the original force or component. This one is what we call a vector diagram. This one is also a vector diagram. So here, for you to draw this one, we're going to have this force, going to have a normal force, Fn, and a gravitational force, which is Fg. Or, remember, if there is a force which have components, you choose whether you want to write it in component form or using the original force. Then here we're going to have normal force, Fg parallel, Fg perpendicular. This, they are awarded 1 mark. This is 1, 2, 2. You see, this is what we call free body diagram. To draw a free body diagram is very, very much simple. You identify it with the object, you indicate it with what? A dot. Then the forces are the forces that are acting on that particular object. Then let's look at Newton's first law. Newton's first law is states that a body will remain at its state of rest unless a non-zero resultant force acts on it. That means F net is equals to 0. And always F net is equal to 0 at balanced forces, at stationary, at equilibrium, at rest, at constant velocity. You see, so in these conditions, F net is equals to 0. And if F net is equal to 0, there is something called no movement, meaning the objects, they are not going anywhere. There is no movement between the objects. For example, if we have an object in a horizontal plane like this, moving in this direction, moving, right? F net in terms of x is not equal to 0 because the object is moving. But F net in terms of y is equal to 0 because the object is not going upward. It's moving horizontal. Again, if you have an object falling horizontally, moving downwards, meaning the F net y is equal to, not equal to 0 because it's going down, but F net x is equals to 0 because of what? The object is not moving horizontal, but it's moving downward. You see. Then from there, you can take in consideration of everything. Then this was Newton's first law. Let's go again and look at Newton's second. This is just a summary, remember. We already did these things in class. And Newton's second law. It says when the resultant force acts on an object, the object will accelerate in the same direction of the force. with an acceleration that is inversely proportional to the mass of the object, but directly proportional to the force of the object. I just switched it around, but something like this. Okay. So here we have a force called F net is equals to MA. This definition, because this one and this one did not have banner like this. F net is directly proportional to A. Which are directly proportional. It means if F net increases, acceleration increases. If F net, for an instance, decreases, acceleration decreases. Always like that. If F net increases, acceleration increases. If F net decreases, acceleration decreases. Graphically, it's going to be written like this. F net, acceleration, directly proportional. This is a directly proportional graphical representation. Graphically. Jesus Christ. This is the first situation. This is the second situation. So in the second situation, they're telling us if we can solve this, F net is equals to M, which is equals to A. They're telling us that acceleration is inversely proportional to mass. Inversely proportional to mass. Meaning when mass increases, when acceleration increases, mass decreases. And when acceleration decreases, mass will eventually increase, you see, in opposite direction. Then graphically it would be F net. Then here it will be 1 over M, straight line. Or it can be F net M, being like that. So that it will be the whole relationship of this formula. Let's look at further things in here. So we'll be looking at something called tension. In tension, it works like this. If they tell you about something called an inextensible string, when they talk about string, they're telling you about tension. When they're talking about this, they're telling you about no weight. So if we have an object here and another object there, always there is tension. T. The tension which is equal to negative T. The tensions are equal but in opposite direction. They always say like that. Tension are equal but in opposite direction. They're always like that. They're always equal, but they're in opposite directions. So if we have a horizontal plane like this, and we have an object and another object, and this, we also have tensions. Tensions that are equal but in opposite direction also applies in this one. Even if you have an object in an incline, there is a tension here, this terrain. Tensions are always equal but in opposite directions. If you have a pulley, something like that, there is always a tension there. Tensions are equal but in opposite direction. See? Yeah, that is all. Then let me share a class activity based on vectors in two dimension. Vectors in two dimensions. Okay. So here we have a situation. They're saying learners doing a force. Oh, damn, crazy. Sorry about that. Yeah, learners doing a force board practical finds the following forces could balance A. Immediately they talk about balance, they're talking about F net is equal to 0. So based on everything that we did, they says what is the magnitude of the resultant force of the system? They said balanced. And remember, the time I shared uh, certain pages here, I told you about being at rest. If Fnet is at rest, there is balanced forces. Then that thing eventually came out. What, how about what is the magnitude of the resultant force? Meaning it is 0 neutrons. Let me see before I start to write things that are not there. Is 0 neutrons. State the Newton first law in weight. State that when the resultant force, state that when this is state a Newton's law in weight, you have to stand and say Newton's law, first law, state that a body will remain at its state of rest unless a non-zero resultant force act on it. Then it will be our full definition of basically what is stating Newton first law. Then we've got the remarks. It says calculate the components of the forces. Remember here we've got a vertical component and got also a horizontal component. In vectors in two dimensions, I advise that always before you find the component, use SOHCAHTOOL tool. This is your key, SOHCAHTOOL tool. If you can check here, let me erase what I've already written here about the first law. If you can check here, we have, sorry about that. We have, this is our horizontal component T1 X. This is our vertical component T1 Y, right? So the components, they're both vertical and horizontal. So what I advise is this is theta, this is angle. Remember, always when they're talking about components, they're telling you about sine and cos. So we're always using this. Firstly, we're going to say sine theta, which is this angle, is equals to opposite is this one, which is T1 X over hypotenuse, which is T1, which is T1. Then sine, then here we're gonna multiply everything. Sorry about that. We're gonna multiply everything. Gonna multiply this by that. We'll be having T1 X, which is equal to T1 sine theta. Then T1 X, it will be equal to T1 is 381.05 sine 60 degrees. You see, then T1X is equal to the number that you get Newton. This is our horizontal component because this is the opposite. That is how we find it. Then cos theta. Remember, component is sine and cos. That's the only thing that you need. Is equals to adjacent T1Y because this is between the angle and the 90 degrees. T1Y divided by T1. Then T1Y is equal to T1 cos theta, which is equal to T1 is 381.05 cos 60 degrees. Then you're gonna get your horizontal component. Then you get all of your 3 marks, 1, 2, and 3. So again, 2.2.2, which is this one, the components of STEM T2. We're gonna start here and say, going that side, it is T2x. Going this side is T2y. Then because of this angle, we're gonna use sine theta, which is equals to opposite, which is T2x, hypotenuse, which is T2. Then it's gonna be T2x equals to T2 sine theta. Then T2x is equals to 660 sine 30 degrees. Then T2x is equals to whatever you get, Newton, 2 marks, 1 mark. Then we come again and say cos. Remember, the components, they're always going to hand with sine and cos. Then we're going to come and say cos. Sometimes sine goes hand in hand with the y component. Sometimes cos goes hand in hand with the x component. But it depends on the situation and how a triangle is standing. If you can check here, the triangles are standing somehow. That's why the components are switched. So we're going to say cos theta is equals to T2y divided by T2. This thing is going to be T2y divided by T2 cos theta. Then you substitute to 660 Newton cos 30 degrees. You see, that is how. Then the last one is the mass. The mass. The mass. The mass. The only thing is just that I wasn't finding the answers here. So when it comes to calculating the mass, it's gonna be another situation. But I'm gonna simplify it. Okay. When we calculate the mass, which is 2.3.3, it goes like this. Remember, for me to find the mass here, the object is balanced, meaning F net y and F net x. Where F net x is equal to F net y, which is equal to 0. All of them, they're equal to 0. All of those components are equal to 0. That's why. So here, for us to find that, we need to know that Fg is equal to mg. And for us to find the mass, meaning we have to focus on all vertical forces. Meaning we're going to say F net y is equal to 0 because it's not going anywhere. Then we're going to say upward is positive, downward is negative. Upward, we're going to have T1y plus T2y minus Fg is equal to 0. Then this one, we have the answers for them. We calculated them somewhere there, but just lost the count. Then it's going to be negative Fg, which is equal to negative T1y plus, negative T2y. That means negative M 9.8 because of G. Remember, is equal to this. G is 9.8 is equal to negative T1y redefined the label. So just take them and substitute them here, which is T1y minus T2y. Then you divide M is equal to negative T1y minus T2y is equal to negative 9.8. Then you take the values, substitute them there, then you get your answer, which is M, which should be equal to, I don't know. But let me go through my calculator and try to find the values. Okay, we got 660 cos 30. We got negative 1. to be plus 362.92. No, let me just do this. Then you will just find your answer here, kg. Angere the values jai, the value yam. Kelo ya T1Y is this one there. Ya T1, T2Y is this one there. It's just that I didn't make use of my calculator, but to make sense of everything. So yeah, that we came to the end of today's series. So, I mean,